Hello everyone, my name is Austin Rovinsky, and I'm an assistant professor at New York University. This is the 6th lecture in my mini-course on physical design databases, and this lecture will continue on OpenDB classes. This time, we will be focusing on the classes for wires and routing. Last time, we covered the master data stored in the libraries and the instance data stored in the DB block. These two combine to form all of the information about instances and terminals in the design. This time, we're going to focus more on the physical connections between these instances and terminals, which are formed by routing and wires. Just like how masters store common information in the DB lib, the DB tech is going to store common technology information. Then, the DB block is going to store the information about all of the nets in the design and the geometries associated with them. Navigating inside the DB tech, we'll find that the two main components in here are layers and vias, as well as some others. Remember that every chip is going to have specific properties defined for each layer, mostly dealing with the design rules such as how wide or narrow your wires can be, or how close together can you put two separate wires, and many more rules like that. For vias, we have this idea called technology vias, which are a predefined set of vias that you can make connections to between layers. The idea here is that in the technology left, we will have a curated set of these vias, which are known to work well during routing. So these DB tech vias are really just storing these predefined vias. That covers most of the technology side of things. A vast majority of the data in DB tech is going to be stored in the various technology rules, but these are beyond the scope of this course. The next part is identifying all of the nets in the design. As discussed in the previous lecture, there are many other elements in the DB block, and the nets are one of them. Remember that the nets are just the logical connections between different terminals. Some of these terminals could be from instances, and some of these terminals could be inputs or outputs from the block. So the DBNet has a list of pointers to both the I terms and the B terms it's connected to, if any. It also acts as a container for the physical shapes associated with the net. There are two main classes here, DB-wire and DB-S-wire. DB-wire is for normal wires, which are used to route digital signals. And the DB-S-wire is used for so-called special wires, which are essentially just anything or any wire or net which is not routed by the digital routing tool. So this will commonly include power and ground wires for delivering power to instances. DB wire and DBS wire are fairly similar, so I'll discuss just DB wire here. DB wire is composed of a sequence of DB shapes, where a shape is more or less just a rectangle with a technology layer attached to it. These DB shapes are not stored conventionally, actually. They are transformed using a wire encoder class. And the reason behind this is that it optimizes how much space these objects take up, because there could be millions of these objects in the design. So if your code needs to access these DB shapes, typically you'll create an iterator using the wire encoder class, which will let you iterate over all of the shapes inside the wire. As a brief addition, I want to also talk about some objects related to placement, which instances are allowed to be placed on the chip. When masters are designed, they're generally designed such that they have a fixed height and an integer multiple width. The reason for this is that they can stack together nicely, almost like Lego bricks. We call this fixed height and integer width a cell site. These sites are essentially the minimum granularity that you can place a cell on your chip. Just like in Lego, you could place your brick on the bumps and you can move it around an integer number of those bumps, but you can't place a brick between the bumps. And a very similar idea applies to cells or instances and the cell sites that they get placed on. So if we use these cell sites to create placeable slots over our whole chip, we get the structure that you see here. Each cell is tiled across the chip, and sites are grouped together into cell rows. Multiple rows are stacked together, and that forms all of the slots where instances can be placed on the chip. And both of these are stored inside the DB block too. All of the rows are stored in the block, and then each row stores the location, the size of a cell site, and the number of sites. The DB row doesn't store each site as an individual object, but a compressed format because it's rather easy to derive the cell site locations from this method without using all the extra memory. So that wraps up everything for the second part of OpenDB classes. The things to remember here are that routing is broken up into two areas. The rules are stored in the DB tech, whereas the actual wire shapes are stored in the DB block. One overall takeaway from the last two lectures is that we try to deduplicate information. So any common information like vias, masters, routing rules, all get stored in either the DB lib or the DB tech. And then we have unique information like instance locations or wire routes, and those will be stored in the DB block. So that's all for this lecture. I'd like to take a moment to thank Nordtech, who has provided the funding to make this mini course possible, and thank you for taking the time to watch it. I'll see you next time.